We are going to start from the representation theory of the Lorentz group to derive the Lie algebra of the group. In particular, we are going to start from the composition rule of the representation of Lorentz transformations. We can consider a certain Lorentz transformation and we call it lambda, capital lambda, and then we associate a certain representation to this matrix. This is a matrix, and we can call the representation U, so it will be a function of lambda. When you can think of U as a unitary operator technically, but basically it is another matrix if you want to think about it in an informal way, in some kind of informal way. So we have another matrix, and we can use the following rule. So for example, if we have the unitary operator associated to the product of two Lorentz transformations, so lambda prime times lambda, this would be the representation of lambda prime times the representation of lambda. This seems a very simple rule, quite intuitive rule, but this is quite important because we will derive exactly, starting from this rule, the so-called Lie algebra of the Lorentz group, which is something related to angular momentum and to other operators like momentum, as well as boosts operator. And now we can also write down another rule of the kind U of lambda inverse, so the representation of the inverse of a Lorentz transformation is equal to the inverse of the representation. So in particular, we will use both of these in the following for the following formula. So we have U of lambda inverse lambda prime lambda. This is equal to U of lambda inverse U of lambda prime U of lambda. Now we are going to rewrite lambda prime as an infinitesimal transformation, so it will be equal to something close to the identity. I will call it 1, but this is actually an operator, the identity operator, plus a small infinitesimal, so this is an infinitesimal transformation which I will call delta omega prime. And you have to remember that in the case of infinitesimal Lorentz transformations, this object here is anti-symmetric, so if we use the index notation, we would have two indices, alpha and beta, because it can be treated as a matrix, which is equal to minus delta omega prime beta alpha. So we can rewrite lambda inverse lambda prime lambda by using this formula here. So this can be written as, so if you replace this formula there, for lambda prime, you get something close to the identity plus lambda inverse delta omega prime lambda. Then for an infinitesimal Lorentz transformation, U of lambda prime would also be something close to the identity. So this would be U of 1, so this is the identity operator, plus delta omega prime. We define it to be the identity plus a small perturbation, which we write in the following form: I over 2 delta omega mu nu m mu nu, like this. So we have to sum over mu and over nu here, and this is the way in which we expand this term here. So we basically, this implies that we have inserted this m mu nu, which is related to the expansion of this operator here, where m mu nu is equal to minus m nu mu. So it is an anti-symmetric operator. Now we want to use such expansions to rewrite this formula: U of lambda inverse U of lambda prime U of lambda, which appears here. So if we do that, if we rewrite this by inserting this expression, we get the following. So we get u of lambda inverse u of lambda, because we have replaced this with this, so the identity must be inserted there, so we get this first term plus another term that contains this, so we have plus I over 2 u of lambda inverse, then we have delta omega mu nu m mu nu u of lambda. And this, remember, must be equal to u of lambda inverse lambda prime lambda. And we can rewrite this in the following manner by substituting the expression for lambda prime. Remember that lambda prime is an infinitesimal Lorentz transformation written like this. So we can substitute it and we obtain the following. We have u of the identity plus lambda inverse delta omega prime lambda, and this is equal to 1, so the operator 1 plus I over 2, and then here we have lambda inverse rho a delta omega prime AB lambda B sigma M rho sigma. So I have used this formula here, where instead of 1 plus delta omega prime, you have to imagine that we have this expression. So instead of delta omega prime, we have this, lambda inverse delta omega prime lambda. So the expression is really this one, which multiplies m rho sigma. Now, to be rigorous, here in this expression, I should use omega prime mu nu, because it's the same as this expression here. So here I have delta omega prime mu nu, and similarly, in here I have delta omega prime mu nu, to be rigorous and to avoid any kind of confusion. Now, let me manipulate it a little bit more. In particular, this term here is equal to lambda a rho written like this, with a different order of these two indices. And why is this? The reason is this. Lorentz transformations satisfy the following property. Lambda mu rho era mu nu lambda nu sigma is equal to eta rho sigma, like this. And since this relation here is valid, we can also rearrange these terms in the following manner. In particular, this is written in index notation. If you want to write it in matrix notation, this would be something like lambda transpose era lambda equal to era. So this means that lambda transpose era is equal to era lambda inverse. And if we go back to index notation, this would be lambda alpha beta era alpha gamma equal to era beta alpha lambda inverse alpha gamma. And now if we use the usual rules for tensors, if we multiply a tensor by the metric tensor, we can raise and lower indices accordingly. For example, in here we can rewrite this as lambda gamma beta, and here we can write it as lambda inverse beta gamma. And so these two are equal, and if you want to, you can also write it with mixed indices by an appropriate multiplication with the metric tensor. This can be written as lambda gamma beta equal to lambda inverse beta gamma. And this proves this relation. So this is equal to this. Now notice that in here we have u of lambda inverse u lambda, which is of course equal to the identity operator, and now we can equate, so this must be equal to this. And if you set them equal to each other, what you get is the following expression. So you get u of lambda inverse m mu nu u of lambda equal to lambda mu rho lambda nu sigma m rho sigma. And this is an important relation. In the subsequent part of the video, I will show you how to rewrite this expression, so how to derive, starting from this expression, the Lie algebra of the Lorentz group. So let's manipulate this formula here. In particular, let's start from the left-hand side of the expression, and we rewrite the left-hand side by using the usual rules for infinitesimal transformations. Let's start with the u of lambda. This one here was defined like this. Identity plus I over 2 delta omega prime, but now let's drop the prime here for convenience. And so delta omega is equal to delta omega prime. Think about it in this way, but it is just for sake of convenience, I want to avoid writing the primes. So delta omega AB MAB, we can write it like this. And what about u of lambda inverse? Well, it would be the inverse of this expression. And to first order, it would be exactly the same, but with a minus sign here. So 1 minus I over 2 delta omega. In here, in principle, you have to use different indices. For example, you can use a CD, MCD, like this. So let's rewrite u of lambda inverse m mu nu u of lambda. So we have the identity minus I over 2 delta omega. So we can either use CD or other indices. Since they are dummy indices, the important thing is to differentiate these indices from these indices here. So you don't have to mix them, because otherwise you would be summing over mixed quantities, which is not correct. You have to sum only over this and only over this. So we have the usual rules for tensors: delta omega AB MAB, then we have M mu nu, and then we have the identity plus I over 2 delta omega CD MCD. Let's rewrite it. We can write it as M mu nu minus I over 2 delta omega AB MAB M mu nu identity plus I over 2 delta omega CD MCD. Then we multiply them and we discard the terms which are higher than the first order, so we keep only all terms up to the first order in the omegas, in delta omegas. So we have M mu nu minus I over 2 delta omega AB MAB M mu nu plus I over 2 M mu nu delta omega CD MCD, and we can rewrite it like this: M mu nu plus I over 2 delta omega CD M mu nu M CD. Then we have minus delta omega AB MAB M mu nu. Then we can rewrite it in the following fashion: M mu nu plus I over 2 delta omega rho sigma. And then we have a commutator between M mu nu M rho sigma. So basically you can change the dummy indices by relabeling C and D, for example, like this. You have C becomes rho and D becomes sigma, so here as well. And here A becomes rho and B becomes sigma, and here as well. So you have M rho sigma, which multiplies M mu nu. And if you check, you have exactly the commutator there. Now we want to rewrite also the other term on the right of this expression, so this term here, and we write it like this: lambda mu rho lambda nu sigma m rho sigma, which is equal to, now we can also rewrite it like this: lambda mu a lambda nu b MAB, by relabeling the indices. Now we use the usual infinitesimal transformation, so we have the identity here, but in this case, since we are using these indices, the identity becomes the Kronecker delta mu A plus the small change delta omega mu A, not mu alpha. And then here we have delta nu B plus the change omega in omega nu B times M AB, like this. Now we can do some multiplications there. We have delta mu A plus delta omega mu A. If we multiply by MAB, we have M A nu plus the change in omega nu B MAB, which is equal to M mu nu. When we multiply this by this, then we have other terms plus delta omega LB. Then we use the metric tensor, the Lorentz metric tensor, so era nu L M mu B. So this comes from the multiplication between this and this. Then we have another term plus the change in omega MA era mu M A nu, and then you have higher order terms that you can neglect. So in particular, I'm referring to the multiplication between this and this, which you can neglect because it is a second order term in delta omega. Now we can rewrite this expression in the following manner. We have M mu nu plus 1/2. I will put this 1/2 because I'm going to rewrite this term twice and this term twice by relabeling appropriately the indices. So you can check that you can rewrite it as delta omega rho sigma. So let's put a bracket here. Then we have era nu rho m mu sigma plus delta omega sigma rho era nu sigma m mu rho plus delta omega rho sigma era mu rho m sigma nu plus delta omega sigma rho era mu sigma m rho nu. Now I'm going to rewrite one more time like this. I will make use of the property of the anti-symmetry property of delta omega. I have plus 1/2 delta omega rho sigma era mu rho m sigma nu plus era nu rho m mu sigma minus era mu sigma m rho nu minus era nu sigma m mu rho, and that's it. At this point we have shown that this must be equal to this expression here. Since these variations here, these small changes are arbitrary, they are infinitesimal and arbitrary, we have basically shown that the commutator between m mu nu and m rho sigma must be equal to I. We have this expression, but we have to change the sign of it because I have multiplied by I. If you remember, we have a factor of I in here, which is just used as a definition when we expand these terms. You can see that we have a factor of I, but it is something that at the end of the day we have introduced. Sometimes, some other times, it is you might see in other references, in some books or in some papers, you might see a different definition of such expansion. So you might see some factor of I disappearing and different signs, but I hope that you can follow the logic to understand where the Lie algebra comes from. So it is really something that comes from the representation theory of the Lorentz group. Now let me finish writing this expression, conclude the video. So I have I times era mu rho m nu sigma minus era nu rho m mu sigma minus, and then here we have era mu sigma m nu rho, and then we have plus era nu sigma m mu rho. And this is exactly the Lie algebra of the Lorentz group, which contains the commutator between the boosts and angular momenta, because this can be split further, since this operator here is a generic operator of angular momentum, but it is a relativistic operator of angular momentum. It can be split further to show non-Lorentz invariant expressions of the commutator by defining the angular momentum operator J and the vector of boosts K. For example, J, let's write it in index notation. Ji would be something like this: 1/2 the Levi-Civita symbol epsilon I jk and jk. By using this definition, one can show, for example, that we have the usual commutation rule that one encounters in quantum mechanics. So the commutator between Ji and Jj, so this is not really a nice way of writing it, because this index is the same as the letter we use for angular momentum, but whatever, this is the index, it would be I epsilon I jk. So we have the usual commutation rule for angular momentum, which can be derived from the Lie algebra written in covariant form like that.